Hello and welcome to Lecture 5, 1D Kinematics. In this lecture, we're going to discuss scalar versus vector quantities, and we'll be able to distinguish between the two. We're going to introduce some of the kinematic equations. So we're going to have 3 kinematics equations that are introduced today, and we're going to use them to solve problems, kinematics problems. We'll also use them to solve kinematics problems that involve gravity. And then we'll solve a special type of kinematics problem where one object is catching up to another. All right, so what's the difference between a scalar and a vector quantity? So in the last lecture, we talked about vector quantities. Vector quantities are quantities that have both a magnitude and a direction, whereas a scalar quantity only has a magnitude. So I'm just going to fill that in here. A scalar quantity is one which only has a magnitude, whereas vector quantities have a magnitude and a direction. All right, so we're going to classify each of the quantities in the table below as either a scalar or a vector, and we'll give an example for each. So for example, the first quantity is distance. Okay, so distance is how far you're traveling. So let's say the distance from my house to the school is 20 kilometers. 20 kilometers. All right, so this is the magnitude over here. There is no direction. I didn't say which direction I have to go to get to the university. I just gave you the distance between my house and the university. So this would be a scalar. So I'll just write S for scalar. All right, speed. So let's say I'm driving, on average, my speed to get to work is 60 kilometers per hour. That's my speed. Again, there is no direction here, so that means that speed is a scalar quantity. Okay, then we have time. So time just means how much time does it take to do something. So for example, it takes me 20 minutes to get to work. Okay, so then if it takes me 20 minutes to get to work, then there's no direction involved there at all. So that would be, again, a scalar quantity. Okay, then we move on to displacement. So displacement is much like distance, except you have to give basically the distance it takes to get somewhere, but also including the direction. So for me to get to work every day, for example, let's pretend I'm driving 20 kilometers, but I'm traveling south. Okay, so my displacement is 20 kilometers south. So that would be then a vector because it includes both a magnitude and a direction. So this would be a vector quantity. Velocity. So again, velocity is much the same as speed. It just means how fast you're going, but you're also giving a direction. Now, direction can be south, east, northwest. It could be east 30 degrees north, for example, but it could also be up or forward or backward or down. Okay, so there's a lot of different examples of directions. It could be also 30 degrees above the x-axis, the positive x-axis. So these are all examples of directions. So let's say my velocity when I'm driving up to the cottage is on average 100 kilometers per hour, and we're traveling north. Okay, so that would be my velocity, and that is a vector because there is both a magnitude and a direction. Okay, so that's a velocity. Acceleration. So acceleration is how fast your speed or your velocity is changing over time. Okay, so let's say you are parked in your car, and so your velocity at that moment is 0 kilometers per hour, but then after 1 second, you've accelerated and you're now traveling 5 kilometers per hour. So in 1 second, your car sped from 0 kilometers per hour to 5 kilometers per hour. That would mean that your acceleration is 5 kilometers per hour per second. Okay, so in 1 second, you accelerated, or your speed changed by 5 kilometers per hour. Now, if you're traveling north and your speed is increasing, then your acceleration would also be north. All right, so acceleration is a vector. You should be including both the magnitude and the direction. So acceleration is a vector. Okay, if we were to talk about SI units for all of these things, the examples that I've been giving are not in SI units, right? So for each of these, if I were to put in the SI units for distance, the SI units are meters. For speed, meters per second. For time, seconds. For displacement, meters. And then a direction. I'll just write DIR for direction. Velocity, meters per second, and then a direction. And acceleration, the SI units are meters per second squared, and then a direction. Okay? All right, mass. So mass is, for example, my mass might be something like 75 kilograms. Okay, the SI unit for mass is kilograms. Force. All right, so this would be like a force that's acting on an object. Let's say the force acting on an object is 30 newtons. Okay, so if we go back to mass, does that 75 kilograms have a direction to it? It doesn't. It's just a mass. This is just how much something, like the amount of mass is in something. It doesn't have a direction to it, so it is just a scalar value, no direction. But a force actually does have a direction. It points in a certain way. So forces are vector quantities. So let's say 30 newtons down would be an example of a force acting on something. So I pull on something downwards, there's a force acting on it of 30 newtons down. Okay, so newtons is the unit, the SI unit for force, and you have to give a direction. So because force has both a magnitude and a direction, it is a vector. All right, and then we have energy. So I had a bowl of cereal this morning. It was 200 calories of cereal and milk. That's energy. There's no direction to it. Okay, the SI unit for energy is the joule. No direction, so it is a scalar. All right, so I hope that all made sense. It's really important that you can distinguish between scalar and vector quantities, because if, for example, I ask you for distance, I only want the magnitude. But if I asked you for displacement, okay, distance and displacement are very similar. They're both measured in meters in SI units, but displacement, I expect you to give a direction. Likewise for velocity, for acceleration, and for force. Okay, so make sure you're including directions for those vector quantities. All right, so now we're going to introduce the 3 kinematic equations that we're going to be using throughout this course. And these equations are provided for you on your tests and exams, so you don't have to memorize any of them. The equations are only valid when acceleration is constant. All right, so if the acceleration is not constant in a question, you can't use these equations. So in this course, anytime you have to use one of these equations, we're assuming acceleration is constant. Okay, so we have a bunch of different terms or variables in these equations, and I just want to make sure that you understand what each of them are. So let's start off with SI. Okay, so SI is over here. All right, so SI means the initial position. So an object's initial position. Okay, so the S is position, and the I stands for initial. All right, next, SF. SF. So what do you think that stands for? Instead of an I, it's an F, so it's final. Final position. And you'll see SF in the first equation there. All right, next we have delta S. Delta S, so delta S, you see it over here. Oops. All right, so what does delta S? Well, the delta, which is this triangle over here, stands for change in. Change in. And the S is position. So delta S is the change in position. So if you were to think of a ruler, and let's say we're at the 1 centimeter mark here, 2 centimeter, 3 centimeter, 4 centimeter, 5, 6, let's say this is 7, and it keeps going. Let's say we started off over here. That would be my S initial, which is 2 centimeters. And let's say I finished off somewhere over here. So let's say that would be my SF, then my final position is 7 centimeters. So then my change in position, what would that be? It's the distance that I've traveled, the change. So I went from 2 centimeters to 7 centimeters. So my delta S is always equal to S final minus S initial. So 7 minus 2, which is 5 centimeters. So that's the distance that I traveled right here. That's my delta S. Okay, so delta S is the change in the position. How far did you actually travel? Okay, now let's move on to V. V initial. So V over here, V initial, we see it again over here, and we see it again over here. Okay, so V stands for velocity and I for initial. So this would be initial velocity. Okay, then we have V final. So V final, VF, V again for velocity, and then F for final. So we have final velocity. All right, now we have acceleration. So here's acceleration right here, here, here. Notice acceleration is in every equation. So in order to solve any kinematics problem using any of these equations, you need to know the acceleration. All right, so the acceleration, that's all that is. I'll just highlight it so it corresponds. And then finally, we have delta t. Delta t. So you have delta t here, and we have delta t here, we have delta t here. Okay, so two of the equations have delta t in it. What does delta stand for? We already said before that little triangle means change in, and then t is time. So delta t is change in time. All right, so there's my delta t. Okay, so what that means is, let's say my initial time, so let's say I'm running a race and I start the race at 5:15 p.m. and I get to the end of the race, so that would be my initial time, t initial. I get to the finish line at 5:23 p.m. Okay, so that was my initial time, my final time. My change in time is when I subtract the two. 5:23 minus 5:15, so that's 8 minutes. So delta t, the amount of time that went by from when I started to when I finished, is 8 minutes. Okay. All right, so let's practice using these equations on the following word problems. Okay, so we have an airplane that's accelerating from rest down a runway at 3.2 meters per second squared. So before we continue, let's identify what that variable is, 3.20 meters per second squared. Okay, actually what we could do is we can go through all the variables we discussed above, and let's write the SI units for all of them. So position, SI unit would be meters, final position still meters, and change in position still meters. They're similar to distance. V initial, so that's our speed or our velocity, meters per second. V final, still meters per second. And now acceleration, meters per second squared. And time is just in seconds. It's really important that you know what the units are for each of these, because sometimes in a question, it won't tell you what the variable is representing, but you can figure it out by looking at the units. So when we look at question 2 and it tells us the airplane accelerates from rest down a runway at 3.2 meters per second squared, well, we can identify those units as being the units for acceleration. So that is our acceleration. For 32.8 seconds. Okay, that's the amount of time that's gone by. So that is our change in time, delta t. 32.8 seconds until it finally lifts off the ground. Okay. Determine the distance traveled before takeoff. This should say it. The distance traveled before takeoff. So this is how far it's traveled. It's not the initial position. It's not the final position. It's the change in position. It's how far it's traveled. Just like in this ruler example, we started off at 2 centimeters. We finished at 7, but the distance traveled is 5 centimeters. So we're looking for delta S. That's our question mark. That's what we're looking for. Okay, so the next thing that we're going to do is identify which equation we're going to use to solve this problem. We are looking for delta S. We know A. We know delta T. Okay, so let's take a look at our 3 kinematic equations and identify which one is it that we want to use. Okay, delta S, delta T, and we're looking for, and A. So we want an equation that has A, delta T, and delta S in it. Now, one thing before we continue, this first equation, it's going to be given to you the way you see it here, SF equals SI plus VI delta T plus 1/2 A delta T squared on your tests and on your exam. But you can recognize that if you were to bring this SI to the left side of the equal sign, the equation can be written as SF minus SI, because remember, when you move something to the opposite side of the equal sign, it changes its sign, equals V initial delta T plus 1/2 A delta T squared. Now, what is SF minus SI? It's equal to delta S. So that equation is the same as delta S equals V initial delta T plus 1/2 A delta T squared. Okay, so keep that in mind when you're doing problems. If we look at this question does not have anything to do with V in it. Oh, actually, there is one thing we missed. Let's see if you can find it. It says an airplane accelerates from rest. So that is actually giving us a piece of information that we had missed. What information is that? It's telling us that the airplane starts at rest. So what does that mean? It's resting, it's not moving yet. So its initial velocity is 0. V initial equals 0. And I'll put in the units, meters per second. Okay, so that's actually something that's really important to keep in mind. Sometimes it seems like you don't have enough information in a question, but there's sometimes terms like that from rest that gives you more information, but it's not so explicit. Okay, so now we have an extra variable. What is the one variable here in these 3 equations that you don't see listed in over here in question 1? A, delta T, delta S, and V initial. Which variable is missing? It's actually V final. V final is the one variable that we don't know and we don't want to know. It's not asking us to find it. So this is the variable that we don't want to have in our equation. So the way that I identify which equation to use is I identify which variable we don't have and that we don't want to know, and I find the equation that doesn't have that variable in it. So which equation would that be? Well, equation 2 and 3 both have v final. Equation 1 doesn't, so it's equation 1 that we're going to use. Okay, and remember there were two forms of equation 1. There was SF equals SI plus VI delta T plus 1/2 A delta T squared. But if you bring the SI to the other side of the equal sign, that becomes delta S equals V initial delta T plus 1/2 A delta T squared. So you have to figure out which of those two equations do you want to use. Well, we're looking for delta S, so let's use the one that we created here on the left side. So I'm going to rewrite it. It looks like delta S equals V initial delta T plus 1/2 A delta T squared. All right, delta S is what we're looking for, so it's great. It's already isolated on the left side, so we don't need to rearrange this equation at all. We're just going to leave it the way it is. V initial is 0. I'm subbing in the values that I know in brackets. Delta T is 32.8 plus 1/2. A is 3.20, and then delta T again is 32.8 squared. Okay, notice that the units that were given in the question were all SI units, so I didn't need to convert anything. Now I'm just going to type everything on my calculator. 0 times 32.8 plus 1/2 times 3.20 times 32.8 squared. And I get delta S is equal to 1721.3. And my units, delta S, is the distance traveled, so it would be meters. Okay, the question's asking for distance. Distance is a scalar quantity. I don't need to include a direction. And that's it. That was question 2. So I should change that. That should say question 2. All right. So let's move on to question 3. A girl is running across a track. The girl accelerates at 6.00 meters per second squared. So let's write what that is. It's the acceleration. You can tell because it says she accelerates at that acceleration. It also gives us the units meters per second squared, which are the units for acceleration. So I have acceleration is equal to 6.00 meters per second squared over a distance of 6.90 meters. So that would be my delta S. That's the distance traveled is 6.90 meters. When she reaches a speed of 24.8 meters per second. So she reaches that speed, that would be her final speed. So that would be V final is 24.8 meters per second. What was the girl's initial speed? So we're looking for her initial speed, V initial. That's our question mark. That's what we're looking for. So when you think of the kinematic equations, what is the one variable that is not here listed at all? We don't know it, and we don't care to know it. It's not asking us for it. It would be time, delta T. Change in time. That's the variable that we don't know and we don't want to know. So let's take a look at our 3 kinematic equations and look for the one that doesn't include time. Okay, so equations 1 and 2 both have time in there, but equation 3 doesn't. So that's the equation we're going to use. So let's do that. So equation 3 was V final squared equals V initial squared plus 2A delta S. All right, we're solving for V initial. So let's rearrange the formula so V initial is on its own. So that means we're going to take all of this and move it to the other side of the equal sign. So I have V final squared. Instead of it being plus 2A delta S, it's going to be minus 2A delta S is equal to V initial squared. Now we want to get rid of the squared. So all we have to do is plus or minus square root both sides. So I have the plus or minus square root of v final squared minus 2a delta s equals v initial squared. And I'm just going to rewrite it, so v initial squared. Sorry, it should just be v initial because I square rooted it. So now I'm going to just rearrange it. So v initial is on the left side. It just looks nicer that way. Equals plus or minus v final squared minus 2a delta s. Okay? I really recommend that you rearrange your equation to solve for the variable you're looking for first, rather than subbing in your numbers. But if you can't do this, or if you really don't like doing this, go ahead and sub in your numbers. As long as you're getting the correct answer, it's fine. Okay, so you wouldn't lose marks for that, but I just want to recommend that we do that, so I'll try doing that when I do these videos for you. All right, so now we're going to sub in everything that we know. V initial is equal to plus or minus the square root of v final, which was 24.8 squared minus 2. The a value was 6.00, and delta s is 6.90. Notice that all the units given were SI units. I don't bother to include them in my equation at all. I just put the final answer with units. So now I'm just typing this on my calculator, the square root of 24.8 squared minus 2 times 6.00 times 6.90. And I get v initial is equal to plus or minus 23.07. And the units for that would be meters per second. All right, so now there is a plus or minus in front, and we have to decide which is the correct one. So the question's asking us for speed. Is speed a scalar or a vector? Speed is a scalar. So that means no direction. No direction. Plus and minus kind of indicates a direction. If you say positive, that means you're going in the positive direction, whichever way that you define that to be. Maybe it means forward, maybe it means east or north. And minus means the negative direction. But in this case, we don't care about the direction, so that means we don't care about the sign. You would never put in a negative for a speed, because that would indicate you're going in the negative direction. But speed, when we ask for speed, we're not looking for direction. So I'm just going to get rid of this altogether. My answer is just 23.07 meters per second. That's my v initial. All right, so that's the final answer. The girl's initial speed is 23.07 meters per second. All right, so let's move on to the next page. Gravity. So when an object is thrown straight up or straight down near the surface of the Earth, it accelerates at a constant rate of 9.80 meters per second squared. Okay, this number, you need to know it. So you need to have this number memorized. It won't be given to you. This acceleration is the same no matter where the object is in its path. So let's say I have a coin and I toss the coin up and now it's here. And then the coin falls back down and it gets back to where it was before. So when the coin is on its way up, so let's say right at this position here, it's on its way up, the acceleration of this coin is 9.8 meters per second squared. Now remember that acceleration is a vector quantity, so it has a direction. So we need to include what the direction is. So which way is gravity always pulling objects? Does it pull it up, down, left, right, north, east, south, west? Which way? Which way does gravity pull on things? It always pulls down. So that's the direction of gravity. So acceleration, which is due to gravity, is always 9.80 meters per second squared, pointing down. So when an object is on its way up, like this little coin example here, the acceleration due to gravity is 9.8 meters per second squared down. when the object is, let's say, at its maximum height. So right here, it reached its maximum height. It's going to go down after this. The acceleration is still 9.8 meters per second squared down. And when the object is on its way down, its acceleration, so let's say right here, is still 9.80 meters per second squared down. And it's a common misconception. Some people think that when it's on its way up, the acceleration is up, and when it's on its way down, the acceleration is down, and when it's at the very top, its acceleration is 0, but that's not true. Okay? Wherever the object is in its path, no matter where it is, the acceleration is the same. It's always 9.80 meters per second squared down. So when you have a problem that's a kinematics problem, and you think you don't have enough information, remember the 3 kinematics equations, they all include the variable acceleration. If the acceleration is not given to you explicitly, it may be that you actually know what it is because it's due to gravity, so it's 9.8 meters per second squared down. Okay, so let's take a look at question 4. The observation deck of a tall skyscraper, which is 370 meters above the street. It should say is 370 meters above the street. Determine the time required for a penny to free fall from the deck to the street below, assuming it started from rest. Okay, so let's just draw a little diagram of what's happening here. There's the observation deck of a tall skyscraper, and it's 370 meters above the street. So let's say this is the street over here. We'll say it's at 0 meters. Then this is at 370 meters. Okay, so this is the penny right here. Determine the time required for the penny to free fall from the deck to the street below. So that penny is just falling straight down, and it's going to hit the ground. Okay, assuming it started from rest. So let's write down all the variables that we know here. So the penny starts at the very top. Okay, so if it starts at the top of the of the observation deck, it's at 370 meters, then that would be its initial position. Now we said the bottom, we defined it at 0 meters. The top is 370 meters, so I'm going to say S initial is 370 meters, and S final, the final position where it ends up, is 0 meters. Okay, we're looking for the time required, so that's delta t. That's my question mark. For the penny to free fall from the deck to the street below. So free fall, what that means is that the only force acting on it is gravity. So we know the acceleration. No matter where the penny is in its fall, the acceleration due to gravity is always the same value, 9.80 meters per second squared, and it always points straight down. So now we need to decide, is down positive or is down negative? Now that just depends on how you set up your question. Do you see how the bottom down here is 0 meters and up here is 370 meters? Well, then we're saying that going upwards is the positive direction because we went from 0 to 370. So we said, by setting this up, that up is positive. So since acceleration due to gravity points down, that acceleration must be negative. Okay, so our acceleration due to gravity is negative 9.80. As long as you say up is positive, acceleration due to gravity will always be negative. But sometimes some people change it and they decide to make down be positive. And that would be fine too. One last piece of information, it says, assuming it started from rest. It starts from rest. That means the initial velocity is 0. V initial equals 0 meters per second. All right, so we have S initial, S final. We're looking for delta t. We know A. We know V initial. What is the one variable that we don't know and we don't want to know? V final. That's the one we don't care about. So we need to choose the kinematic equation that doesn't have V final in it. So let's do that. Let's find the kinematic equations. Which one doesn't have V final in it? It would be equation number 1. Okay, so let's use equation number 1. So we have S final equals S initial plus V initial delta t plus 1/2 A delta t squared. All right. And remember, this equation can also be written as delta S equals V initial delta t plus 1/2 A delta t squared. But since we know S initial and S final, we're leaving it in its original form. So we're looking for delta t. Okay, and delta t is written out twice here. One is just as a simple delta t, the other one delta t squared. Because of this, we can't rearrange the equation to solve for delta t. So we're going to just sub in our values right now. So SF is 0, S initial is 370, V initial is 0, delta t is what we're looking for, plus 1/2 A is negative 9.80, and delta t again is what we're looking for, squared. Okay, so let's simplify this a little bit. We have 0 equals 370. This goes to 0 because 0 times delta t is 0. 1/2 times negative 9.8 is negative 4.9 delta t squared. Okay, so now I'm just going to move this over to the other side of the equal sign. Since it's negative right now, it's going to become positive 4.9 delta t squared equals 370. I'm trying to solve for delta t, so I need to get rid of that 4.9. So I'm going to divide both sides by 4.9. And I get delta t squared equals 370. I'm going to type this on my calculator. 370 divided by 4.9, which is 75.5102. Notice I have lots of extra digits here, just because this isn't my final answer yet. Now I want to get rid of the squared, so I'm going to square root both sides. We should have a plus or minus in front. Delta t, when I square root delta t squared, I just get delta t equals, and the square root of 75.5102 is 8.69. Okay, I have my plus or minus. This is time. There's no such thing as negative time, so I'm not even going to include that minus. Time SI units are seconds. Okay, if we take a look at the original question, all the units were SI units, so I didn't have to convert anything. Okay, so that means my answer will also be in SI units, which is in seconds. All right, so that was question 4. It says, how long, or determine the time required for a penny to free fall. So it takes the penny 8.69 seconds to hit the ground. Okay, number 5. A stone is dropped into a deep well and is heard to hit the water 3.41 seconds after being dropped. What is the depth of the well? Okay, so let's draw a little picture here. This is where the stone begins. This is where the stone ends up. Okay, so we're trying to find the depth of the well. So we're looking for this distance here that the stone travels. So that distance would just be called delta S. Okay, so this is like my S initial, this is my S final, and I have a delta S. Okay, now if we're going to say up is positive, and I'll denote that just to make it very clear, up is positive by writing positive is upwards. If up is positive, then what should we expect to get for a delta S? We went from a high value to a low value. So when you subtract, remember we said delta S is equal to S final minus S initial. This one is a small number. minus a big number. When we subtract them, we should be getting a negative value. Okay, so when our final answer is negative, that should make sense to us, why we got a negative value. So let's write down all the things that we know. A stone is dropped into a deep well and it is heard to hit the water 3.41 seconds after being dropped. So what variable is that? That's the amount of time that's gone by. So that's delta t. Delta t is equal to 3.41 seconds. Determine the depth of the well. So that's delta s. That's what we're looking for. That's our question mark, and we should expect to get a negative answer there. All right, we don't have a lot of variables happening right now, so we need to think of what other variables are actually given to us, maybe not explicitly, but we should be able to figure it out from the question. One keyword is a stone is dropped. It's not thrown into the well, it's just dropped. That means you were holding it and then you just let go of it. So what does that mean about the initial velocity of the stone? It started off at 0 meters per second because it was just dropped. You just let go of it. So you were holding it still and then you just dropped it. So that's the initial velocity. The other piece of information that's not explicitly given here is the acceleration. Now, what is it that's making the stone accelerate downward? Why is it moving downward? Gravity. So gravity is the only force that's acting on this object. So it's moving with an acceleration due to gravity. So that means acceleration is 9.80 meters per second squared. But we know acceleration points down. And over here, we said up was positive. So then that means that acceleration is negative, 9.80 meters per second squared. Okay, so now we have all this information. We know time, change in time. We know initial velocity. We know acceleration. We're looking for delta s. What is the one variable that is not here at all? We don't know it and we're not looking for it. V final. Okay, so V final is the variable we don't know and we don't care to know. So now we're going to choose the equation that doesn't have V final in it. And it's just the same as the equation that we used before. So in question 4, we didn't know V final, so we used SF equals SI plus VI delta T plus 1/2 A delta T squared. This time, we're looking for delta S, so we want the equation to have delta S in it instead of SF and SI. So when we bring the SI over to the left side of the equal sign, we'll have delta S is equal to V initial delta T plus 1/2 A delta T squared. Okay, if you feel good about this question, go ahead and try it out on your own. Pause the video and then resume when you're ready to make sure you got the right answer. So delta S is the variable we're looking for, and it's already isolated on the left side of the equal sign. So we're good. We can just start subbing everything in. So we have delta S is equal to V initial, which is 0, delta T, which is 3.41, plus 1/2 A, which is negative 9.80, and delta T again, which is 3.41 squared. All right, so I'm going to type everything into my calculator. 0 times 3.41 plus 1/2 times negative 9.80 times 3.41 squared. And I get negative 56.97769. So I'm just going to say 98. SI units, meters, everything given was in SI units, so I didn't have to convert anything. Now the question is not asking what the delta S was, it says what is the depth of the well. So you wouldn't say that the depth is a negative 56.98 meters. You would just say the depth is 56.98 meters. So I'm going to just write it out as a sentence. Therefore, the depth is 56.98 meters. And that's it. All right, so sometimes you'll notice that when you're writing out all the variables that you know, there won't be enough, and that's because there's some values that are not explicitly given to you. So in this case, there were two of them. There was the initial velocity because it said it was dropped, and also because we know that the only force acting on this stone is the force of gravity. There's also this acceleration here, which wasn't explicitly told to you. You just needed to know what that value is. Okay? All right, so that was question 5. All right, for these next questions, so we have 2 more questions here. For these next questions, we have one object catching up to another. So whenever an object catches up to another, what does that mean that would be equal for those 2 objects? Okay, so think about that. So let's say there's a parked vehicle, and then there's a bike that's riding by and passes the parked vehicle. Then the vehicle drives, it accelerates, and it catches up to the bike. What is it that's the same at the moment that the vehicle catches up to the bike? Okay, a lot of people, when I ask that question, they say the final velocity is the same. But that's incorrect, because if the final velocity was the same, then the bike would still be ahead of the vehicle, because they would be moving at the same speed, but the bike was ahead of the vehicle to begin with, so then it would stay ahead of it. So it's not the final velocity. When one object catches up to another, that means that they are both at the same place at the same time, right? That's what it means when something catches up to something else. They're at the same place at the same time. That means that the final position and the time are equal, not the final velocity. So when you're going to solve problems like this, it's basically like doing 2 problems at the same time. You have 2 different objects. You're going to write all the values for each of the objects, and then you're going to solve for the final position of each object, so SF, and then make those 2 expressions equal to one another. So let's do a question like this, and it will become more clear. Okay, so we have a child riding her bike at a constant speed of 3.5 meters per second. Just as she passes her dad, who is standing at rest, her dad begins to run to catch up to her. He accelerates at 1.5 meters per second squared. The question's asking how long does it take for the dad to catch up to the child, how fast is the dad running when he catches up to the child, and what's the total distance the dad ran before catching up to the child. Okay, so we have 2 different objects. We have a child and we have a dad. So when we write out the variables for the kinematic equations, we want to make sure we're clear of which object is being represented by which variable. So I'm going to make a table to make it clear. So I'm going to write child and dad, just to organize everything so I don't mix up the 2 objects here. And I'm going to write all the variables that are in the kinematic equation. So I have the child is riding her bike at a constant speed of 3.5 meters per second. Okay, so the child's velocity is 3.5 meters per second. So I'm going to write that as V initial for the child is 3.5 meters per second. Just as she passes her dad, who is standing at rest. So the dad initially is at rest. So that means his initial velocity is 0 meters per second. Just as she passes him, her dad begins to run to catch up to her. He accelerates at 1.5 meters per second squared. So let's write acceleration here. The acceleration of the dad is 1.5 meters per second squared. Well, what's the acceleration of the child? The child is riding her bike at a constant speed. That means her speed is not changing. Acceleration is how fast your speed changes. If it doesn't change, then the acceleration is just 0. Okay, so the child's acceleration is 0 meters per second squared. All right, so we know V initial and we know A for both the child and the dad. And then there's no other information that's given here, right? So in terms of SF and delta T, We don't know these values, but we know that because the dad catches up to the child, they reach the same final position at the same time. So the SFs are equal to each other and the times are equal to each other. So I'm just saying that they're equal. So when we do questions where one object catches up to another, the approach is always to solve for SF for both the child and for the dad, and then to set those two equations equal to each other. So let's do that. So we'll start with the child. So the equation for SF, so in this case, we don't know V initial, V final, we don't care to know it, so that's the equation. We're going to choose the equation that doesn't have that variable in it, so it's going to be equation 1. S final equals S initial plus V initial delta t plus 1/2 A delta t squared. Okay, so if we take a look at everything, SF, that's what we're solving for. What about S initial? What's the initial position of the child and the initial position of the dad? Well, it says that the child just passes her dad. So that means their initial positions are the same. They just passed each other. So let's say here's the child. At that same position is the dad. So the dad is there as well, both of them. And then the child moves ahead and the dad is originally stopped, but he has to catch up to the child and he eventually catches up to her. Okay, so then the initial position for both of them, it doesn't really matter what that value is, but they're the same. So we can pick any number we want and make those initial positions the same. I'm going to make the initial position just the easiest number, S initial, which would just be 0 for both of them. So they both start off at 0, so we're saying this is the 0 position right here. Okay, so let's start plugging in all the numbers that we know. SF equals S initial for the child, and we're only looking at the column for the child. Okay, so we're only looking at this information here. S initial, which is 0, plus V initial for the child, which is 3.5. Delta t, we don't know what it is. We just know it's equal to the dad's delta t, so we'll just leave it as delta t, plus 1/2. And then we have A. So the A, the acceleration for the child. The child was moving at a constant speed, so that A was 0. And then delta t squared. Let's just clean up this equation to make it look a little neater. 0 plus anything, the 0 doesn't do anything, 3.5 delta t plus 1/2 times 0 delta t squared. Anything times 0 just goes away, becomes nothing. So we just have SF equals 3.5 delta t. So let's move on to the dad. Okay, so we're going to use the same formula for the dad. SF equals SI plus VI delta t plus 1/2 A delta t squared. And let's sub in everything we know. We're solving for SF equals SI for the dad was 0, VI for the dad was 0, delta t plus 1/2 A for the dad was 1.5 delta t squared. Let's simplify that. We have SF equals 0 is nothing, 0 delta t is nothing. Now we have 1/2 times 1.5, so 0.75 delta t squared. All right, so now we have an expression for the child's SF and for the dad's SF. And we know that their SF, their final position, is equal to each other, and their time is equal to each other. So I'm going to write now an expression that equates the two, makes them equal to each other. SF for the child is equal to SF for the dad. So SF for the child was 3.5 delta t, and SF for the dad was 0.75 delta t squared. All right, so I'm going to bring everything to one side of the equal sign. Oops. And then what's left over here is just 0. And we could have moved everything to the left side of the equals. It wouldn't have made a difference. Okay, so we're trying to solve for delta t here. Notice that delta t is squared and not squared. There's two ways to solve for this. We could factor the delta t out and then solve, or we could use quadratic formula. So we're going to do that. We're going to use the quadratic formula because we have a quadratic here where the biggest exponent is 2 squared. So if you remember, with the quadratic formula, we have an a, b, and a c. The a is the term, or the coefficient in front of the delta t squared, the squared term. So this would be our a. The b is the coefficient, or the number, in front of just the delta t term. That's our b. And then our c is the number that's by itself. So in this case, it's just plus 0 here. That would be our c. Okay, so we're going to use the quadratic formula. And just as a refresher for the quadratic formula, this is the equation. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's the general quadratic formula. That's when you're looking for a variable that's called x. In this case, the variable we're looking for is delta t. So we're just going to rewrite the quadratic formula, but instead of x, it's going to be delta t. So we have delta t is equal to negative b. Now our b is negative 3.5, so negative b would be positive 3.5, plus or minus the square root of b squared. We need to remember to put that negative 3.5 in brackets, minus 4a, which is 0.75, c, which is 0, all over 2a, 0.75. All right. So I'm going to type this onto my calculator. 3.5. I'm going to do it with a plus sign first. So I have 3.5 plus the square root of bracket negative 3.5, close the bracket, squared, minus 4 times 0.75 times 0 divided by 2 times 0.75, and I get 4.667 seconds. Now I'm going to do the same thing over again, but instead I'm going to put in a minus sign over here. Okay, so I'm going to redo it with a minus sign. On my calculator, I can simply just scroll over to the plus sign and just change it to a minus sign. So if you can do that, that makes things a little bit easier. And when I do that, my answer is 0. Okay, so what does 0 seconds mean? The question, what we're solving for right now, is we're finding out when is the child's position the same as the dad's position. Well, we found out their position is the same after 4.667 seconds and after 0 seconds. Well, 0 seconds makes sense because initially they're at the same position because the child just passed the dad, so they're at the same position at the very beginning. Okay, just as she passes her dad. So she just passed him, they're at the same position. So initially at 0 seconds, they're at the same position, and after 4.667 seconds, they're at the same position. The question's asking how long does it take the dad to catch up to the child? So the answer then is 4.667 seconds. That's how long it takes for the dad to catch up to the child. Okay, so that's part A. All of that was part A. So let's move on to part B. How fast is the dad running when he catches up to the child? Okay, so if we want, we can put this 4.667 seconds in this table for both the child and the dad. So we're looking, how fast was the child running? So for part B, what we're looking for is the final velocity of the dad. How fast was he running when he catches up to the child? That's the final velocity of the dad. So that's what we're looking for. So if we take a look at the table, we know v initial is 0 for the dad, and we're only concerned about the dad because the question's asking how fast is the dad running. Okay, so we're only looking at the information for the dad. So his v initial is 0 meters per second. His acceleration is 1.5 meters per second. And the delta t we found was 4.667 seconds. And we're looking for v final this time. So what is the variable here this time that we don't know and we don't want to know? It's actually that delta s. So that's the variable we don't have here and that we don't want to know. Okay, so now we need to think about which equation are we going to use that doesn't have delta s in it. So let's quickly just go back to our list of equations. Which equation doesn't have delta s in it? Or sf minus si, because that's the same. So equation 1 has sf and si, which is the same as delta s if you move them over to the left side. All right, equation 3 has delta s in it, so it's equation 2 that doesn't. So we're going to use equation 2, vf equals vi plus a delta t. Okay, so I'll write that out. vf equals vi plus a delta t. All right, we're solving for vf, so that's great. It's already isolated on the left side. vi is 0 plus a, which is 1.5, delta t, which is 4.667 seconds. And now I'm just going to type this up into my calculator. So it's 0 plus 1.5 times 4.667, and I get 7.0. And that's meters per second. So that's how fast the dad was going. And then we'll move on to part C. And in part C, the question says, what is the total distance the dad ran? So what variable is that we're looking for before catching up to the child? So we're looking for the delta s for the dad. So delta s. So we can take a look at all these variables from part B and use them to figure out what delta s is. Okay, so there's a couple ways to do this. We've already solved for delta s of the dad. So s final of the dad is 0.07 or 0.75 delta t squared. So that's the same as delta s because we know that the s initial was 0. So whatever the s final is, we could just plug in that time that we got. But let's use an equation. So delta s equals, so that's what we're looking for. Because we have a bunch of different values here, there's more than one equation we can choose. But let's say in this case, we don't want v final, and we don't have it, even though we just found it. But let's look at all the other variables. So we're going to choose any equation that has these other variables in it, the vi, a, delta t, and delta s. That's going to be equation 1 that's been rearranged. Okay, so that equation is delta s equals v initial delta t plus 1/2 a delta t squared. And we're doing this for the dad. So we're using all the variables for the dad. That's why we're using the variables in the column corresponding to the dad. All right, so we have delta s is equal to v initial for the dad was 0, delta t for the dad was 4.667 plus 1/2 a, which is 1.5, delta t squared, which is 4.667 squared. I'm just going to type that onto my calculator. All of this 0 times 4.667 is just 0. So I have 1/2 times 1.5 times 4.667 squared, which is 16.3 meters. So the delta s for the dad, the distance that the dad traveled, was 16.3 meters. All right. Okay. Question 7, final question. A bird is flying straight down at 2.4 meters per second. You're standing on top of the CN Tower, which is 553 meters tall, holding a rubber ball. You release the ball just as the bird passes you. How fast will the ball be traveling when it passes the bird? Okay, this is similar to the question we just did. One object, the ball, is catching up to another, the bird. So I'm going to make a table, ball and bird, and we're going to write out all the information that we know. Okay, so the bird is flying straight down at 2.4 meters per second. So we need to decide whether we want to say up is positive or down is positive. Here's the CN Tower, let's say. Okay, this is the CN Tower, and you're on top of it, and it's 553 meters tall. So let's say that's 553 meters. Okay, so if that's the case and down at the bottom on the ground is 0 meters, then this implies that up is positive, because moving upwards, our numbers are getting more and more positive. They went from 0 to 553. So that means that up is positive. So let's say up is positive in this question. So if the bird is flying straight down at 2.4 meters per second, that means its velocity is negative 2.40 meters per second. So I'm going to write V initial for the bird is negative 2.40 meters per second. Now the bird is flying and it's not falling. So we're not assuming that gravity is pulling it down. We're going to assume that the bird is moving at a constant speed of 2.4 meters per second. I can make it more clear in the question by writing at a constant speed of. Okay, so that makes it more clear. You are standing on top of the CN Tower, which is 553 meters tall, holding a rubber ball. You release the ball just as the bird passes you. Okay, so then the initial velocity of the ball, if you just released it, you just dropped it. You didn't throw it, you just let go of it. The initial velocity of the ball is then just 0 meters per second. You release it just as the bird passes you. Okay, so you're at the top here, so your initial position is 0, and we're talking about the ball because you're holding the ball, is 553 meters. And the bird's initial position is also 553 meters because it just passed you. It says, you release the ball just as the bird passes you. How fast will the ball be traveling when it passes the bird? So V final of the ball, that's the question mark. And that's when the final position of the ball is equal to the final position of the bird, and the time that it takes them to reach that final position are also equal. Now there's another variable here that we haven't written that's explicitly told. I mean, not explicitly told, and that's acceleration. The ball is falling due to gravity, so its acceleration is 9.80 meters per second squared. And we said that up is positive, and acceleration due to gravity always points down, so it's a negative. The bird is moving at a constant speed, so its acceleration is 0 meters per second squared. Okay, so what we're trying to do is find SF for both the ball and for the bird, and then set those two equations equal to each other. So let's do that. So we'll start with the ball. So we're going to use, because we don't know, at this point, we don't know what V final is yet. So we're going to choose the same equation we used last time, which was S final equals S initial plus V initial delta t plus 1/2 A delta t squared. Once we find our delta t, we'll use it to find the V final of the ball. Okay, just like we did in question 6, we found delta t first in part A, and in part B, we found the V final. okay, the V final of the dad. Okay, so let's do it all over again in question 7. So SF is what we don't know for the ball, equals S initial for the ball is 553, plus V initial for the ball is 0. Delta T we don't know, we just know it's equal to the delta T of the bird, plus 1/2. The A, the acceleration for the ball, is that due to gravity, so it's negative 9.80 delta T squared. Let's simplify this a bit. So SF equals 553, 0 delta T is just nothing. 1/2 times negative 9.80 is negative 4.9 delta T squared. Okay, so let's move on to the bird. So for the bird, we're going to use the same formula. SF equals S initial plus V initial delta T plus 1/2 A delta T squared. We'll plug in what we know. So SF is equal to S initial for the bird is 553 plus V initial for the bird is negative 2.40 delta T, we don't know, plus 1/2. The A for the bird is 0, and then delta T squared. Let's simplify that a bit. So we have 553 minus 2.4 delta T, and all of this goes to 0. All right, so now that we know the formula or the expression for SF of the ball and SF of the bird, we can now set them equal to each other. So we're going to say SF of the ball is equal to SF of the bird. So SF of the ball is 553 minus 4.9 delta T squared equals SF of the bird, which is 553 minus 2.4 delta T. We're going to move everything to one side. It doesn't matter which side. Let's move it all over to the left side. Negative 4.9 delta T squared. This is going to be a quadratic formula. The largest exponent is 2, so it's quadratic. We're going to move everything to one side, and we're going to go in order, starting with the squared term, then the not squared term, just the delta T, and then just the regular number. So next, I'm going to bring that negative 2.4 delta T to the other side of the equal sign to make it positive 2.4 delta T. And then I'm going to put my 553, that's still on the left side, so it's going to stay as positive 553. And then I'm going to move the other 553 to the other side of the equal, so that's why it's now negative. And on the right side, I'm left with nothing, so 0. I'll just simplify this. Negative 4.9 delta T squared plus 2.4 delta T. 553 minus 553 is just 0. Equals 0. Okay, so now I can solve for this. Again, I can use the quadratic formula, and I can also factor to solve. I'm going to use the quadratic formula. The coefficient, or the number in front of the squared term, is the A value. The number in front of the delta T term is the B value. And the C, there's just a 0 here, so that would be my C is 0. So I'm going to write the quadratic formula, but instead of writing x is equal to, I'm going to write delta T is equal to, because that is the variable I'm looking for. Delta T is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b, my b is 2.4, so I have negative 2.4 plus or minus the square root of 2.4 squared minus 4. A is negative 4.9. C is 0 all over 2 times A, which is negative 4.9. Now I'm going to type all of this onto my calculator. So I have negative 2.4 plus, I'm going to start with the plus sign. Square root 2.4 squared minus 4 times negative 4.9 times 0 all over 2 times negative 4.9. And I get 0. So when I use the plus sign, I get 0. And now I'm going to do it again, but with a minus sign. So I'm just scrolling on my calculator. If you can do that, that will save you some time. And I'm changing the plus to a minus. And I get 0.4898 seconds. Okay, so the time when the final position of the ball was equal to the final position of the bird is at 0 seconds. So that's initially because the bird had just passed the ball, and after 0.4898 seconds. So the question's not asking for the time, it's asking how fast will the ball be traveling when it passes the bird. So we're looking at the ball here. We just found out the time was 0.4898 seconds, and we're looking for this V final over here. Okay, so now we're going to move on. Because we're looking for V final, we now know time. We can solve for V final. So we don't know what distance. We don't know the delta S over here. We know the initial position, but we don't know the final position because the ball's not hitting the ground. We want to know how fast is the ball traveling when it passes the bird. The bird is just somewhere here. We don't know, somewhere between the top of the CN tower and the ground. We don't know exactly where. So we don't know SF. So we don't want an equation that has SF or delta S in it. So instead we're going to use this equation. I'll move down here. V final equals V initial plus A delta T. And we're talking about the ball here. So I'm just going to write the word ball just so it's very clear. V final of the ball is what we're looking for, equals V initial of the ball, which was 0, plus A of the ball, which is negative 9.80, times time, which is 0.4898. And now I'm just going to type this up. So I have 0 plus negative 9.8 times 0.4898. And I get negative 4.8 meters per second. So that's my final velocity of the ball. And that's my final answer. All right, so that was a lot of work. I hope that everything here made sense. Please feel free to revisit any of these questions, rewatch them if you need any help with any of them. And I hope that all helped, and thanks so much for watching. See you next week. All right, bye.